Today we will talk about one important application of machine learning technology, natural language processing. And this is an area where I do my main research at MIT, and I've been working in this area since 1997 when I started my master. And I shall tell that the area dramatically changed in the last 20 years. But even today, if you ask people what do they think natural language processing about, people typically quite understand that it has to do a lot with processing natural language. Everybody in agreement, but the question is how we do the processing. So some people, when they think about processing language, they really think about deep understanding of language, the same way as now you're listening to me and you kind of really understand in context what I'm saying. On the other hand, we know there are lots and lots of applications which they do very simple string matching, and they are also doing natural language processing. Clearly, you know, your email filter on Gmail, if you're using one, doesn't really understand the meaning of your email to decide that it's spam. You know, as we already know, it's like a simple classifier that uses, you know, just word distributional features to say that this is a spam. So and you can see here, this is a pictorial illustration of simply a view on natural language processing when we are doing string matching. But there is still a big question, what does it mean to process language? And when should we be happy with the performance of natural language processing system? And this question actually goes back to the, you know, one of the most prominent figures in computer science, Turing, who posed the question, what does it mean for machine to be intelligent? And language capacity was one of the important capabilities. And the way he said that machines can be intelligent if they can converse with humans in a way where, you know, somebody else who observes this conversation would be unable to detect a human participant from a machine. And I'm sure many of you have heard about the Turing test, where you have a human in one room and machine or another conversant in another room. They try to make a conversation, and then somebody else needs to decide whether it is a machine or not. And there are a lot of competitions about it, and you know, some people already reach the Turing test performance. But the question is a lot, and I want you to think about it when we're thinking of evaluating the system. What does it mean to produce satisfactory performance? And I want to take you back to a system that was developed at MIT before I was born in 1966 by a professor, Weizenbaum, and the system is called ELIZA. So many of you have heard about it because it's really the first kind of dialogue system, and it was doing, it was conversing with a person about their problem. So here you can see, for instance, a woman says men are all alike. Eliza says in what way? And then the woman says they're always bugging us about something specific or other. And then the machine asks, can you think of a specific example? And the conversation continues. So when you start reading it, it looks, wow, it really got it. And it really asked the question that the woman wanted to hear. But if you continue this conversation, and you can find a lot of logs of Eliza online, you will see that it's very repetitive patterns, and machine uses very simple expressions to kind of paraphrase what humans said, or just kind of say these conversation fillers. What was very interesting about the system, that at the time when Weizenbaum developed the system, he deployed it at MIT, and apparently many assistants at MIT, faculty assistants at MIT, got really hooked up to talk to the system. And they developed trust. And you say, how can you develop trust with a machine that does such simplistic things? But this is a question for all of us to think when we evaluate this natural language processing system. What does it mean to develop human-like performance? It is not only what machine is doing, it's what the human participant is doing, and how do they interpret the machine. And going back to our view of the complexity of the tool, I actually borrowed a slide from my colleague from Stanford, Professor Dan Jirafsky, where he, a few years ago, kind of put all the natural language technology in different baskets, and just to tell us how we can think about solved tasks, tasks that we're making very good progress, and tasks which are still plenty hard. So the tasks that are already solved and many of you are using, for instance, spam detection. Another task if you want to extract certain entity, which is called named entity recognition. For instance, if you're looking at Google News, many times they will tell you the names of people in the news or their organization or locations in the news to extract specific categories. Or, for instance, to identify part of speech tags, to discriminate noun from verb. This technology works pretty well. The second group is a particularly interesting group because at the time when I started working in this field, most of this application either didn't exist or were considered so difficult and hard, like for instance machine translation. When I started, to believe that people in a decade from when I started would be already using in masses machine translation was almost like thinking somebody is going to be flying to the moon and having a party there. But today the fact is that machine translation works pretty reliable. Most online services provide you machine translation. And if you don't read any Japanese and the article is in Japanese, maybe the Google translation is not perfect, but this is your only option, and many people find it useful because they come back to it. Another example is information extractions. Those are models which take a text, which is a free text, and translate it into a structured representation. For instance, database. Like let's say in many pharmaceutical companies, you are people, when they have side effects from the drug, they fill out the form, they write their story in natural language, but then it has to be stored in the database so that you can analyze it, so that regulators can see it. So there is this translation from the free text to the structured representation, for instance, to identify the disease, maybe the other drug the patient takes, their age, and so on. So similarly, another applications that now used really like commercially, this is a sentiment analysis application where the goal is to take a document and to determine its sentiment. So in this particular case, again, machines do pretty well. Now let me tell you about applications which are hard. For instance, unconstrained question answering. If we are looking at the questions like, when Barack Obama was born, this is a very simple question because this is called the factoid questions. You can easily find a sentence which will say Barack Obama was born and so on, where the string matching help. But if you're asking some questions which really requires analysis and comparison, let's say you want to know, compare a computer science degree at MIT and at Stanford, where you really need to collect a lot of data to answer this question. This is plenty hard. Another one is summarization, where you want to give to a machine, let's say, a book or an article, and you want to summarize high points of it. Plenty difficult. And yet another one where we made a lot of progress is dialogue. And some of you may be listening to me now and say, how come is it so hard? Like I use Alexa or other assistant. It's true that we develop, fantastic capacity to reply kind of in a very specific domain, but it's not like you can really have a conversation with Alexa, for instance, about the content of your machine learning course. So this is one view, to look at this technology and say those are the three buckets, and now I know how the space looks like. But I would actually argue that this is a wrong classification. And let me tell you why I believe it is a wrong classification. So first of all, it has a lot to do with measurement. Let's start with a task that in a previous slide we kind of put it in the second column, making a good progress. If you're looking at parsing, parsing means understanding syntactic structure of the sentence. Like you want to understand, for instance, here you have a sentence, I ate cake with a fork today. You want to understand that I didn't eat any cake today. But take two arguments, I and cake. And for instance, if you're looking at the phrase a fork is a head and A is a constituent. So this kind of understanding the syntactic structure of the sentence is really an important way towards understanding the semantics. And these structures are used in many applications. So you can look at it and say, on English, if we're counting how many correct arc we've done, we're doing 93.2. This is the numbers when I prepared the slide. I'm sure now they're even a bit higher. If you're looking MSA, it's Modern Standard Arabic, you can see performance is lower, but still maybe acceptable, correct? So it seems that we really are doing great progress. Now, instead of asking you look at the arc at a time, I'm asking you look at the whole sentence. How many times did you actually get the right trees? Now the numbers look very different because you need to get all the arcs right to get the whole tree right. Now even for English, you can see that you are below 30%. So again, it's, you know, the beauty is in the eye of the beholder, so it depends how you calculate your performance. Let's look at machine translation, another interesting example. So year after year, I was taking, since, you know, they put Google Translator online, whenever I teach at MIT my natural language processing class, I always try to run, you know, to run it through machine translator and see the translation. And what you would see, so this is 2015, then there is 2016, and what you can see that even if you don't understand Hebrew at all, and you're reading the translation, yeah, it is a bit broken, but you totally can understand what is it about. Here you have district court in law dismiss the appeal filed by Miriam Fireberg, suspected of taking bribes in the millions to release her from custody, but shorten the detention center. So you can see there is some that we really are not shortening the detention center, but you can really get the main idea of the story, and if you don't read Hebrew, you cannot get any idea. So, and every year it becomes better and better, and I encourage you to try it either on your own language or on some exotic language and see how translation works. People really use it, and it's not like some entertainment tool, though some people use it this way as well. But what I want to tell you, that when we're looking at this example, we're saying, you know, English and Hebrew is like, Hebrew is sort of on the exotic side. Maybe English and French works almost perfectly. You know, there are pairs of languages on which we have a lot of data, on which machine did very well. And we are very optimistic about it. Now let me show you an example of something that works terribly, and which I'm trying year after year, and I'm trying I encourage you to try it yourself. So a few years back, a friend of mine sent me a recipe in Finnish. I don't speak any Finnish, of some food that I really wanted to try to cook at home. And this is a translation that I got out of of Google. Bake the flat rod and cut it into 20 pieces, or roll the pieces into balls and press them lightly. After order, they become flat. You see, it's really not clear what exactly, you cannot follow, you cannot get the gist at all, you cannot cook based on this recipe. And you can be asking, is the problem Finnish? No, the problem is not Finnish, because if I would give to you to translate a new story on Finnish, it will do very well. The problem is the recipe, because most of the machine translation system, I hypothesize, are trained on material which is closer to news. And maybe there are some recipes as part of the training, but they're really not a dominant part. And as a result, we're getting this funny translation. And here, this brings the first point that I wanted to make, that it's not that the task is hard. It is hard in the context of training data available to you. I'm pretty sure that if we take a standard machine translation system and train it on a large recipe archive, it will do a perfect job. So again, the point that we need to remember that the difficulty of the task should always be assessed in the context of the training data available. Let's look at another example to illustrate this point. So I remember that a few years ago, if you see, you know, this victorious performance of IBM Watson on question answering task. And the question which, you know, the machine won and human didn't, was this question, William Wilkinson's An Account of Principalities of Wallachia and Moldavia inspired this author's most famous novel. I mean, who would know? Unless you do, you know, you major in literature, in a particular type of literature, none of us would know. Machine could find an answer. I would let you try it, but you will see that this question is so repeated, it's really easy to find the answer to it. But I decided, because, you know, it's such a famous question now for the reason that I just mentioned, but I just decided to try to do something else. I look at the books that I love a lot, Flowers for Algernon, And I asked the question, what was the inspiration for flowers for Algernon? And you can say, for machine to answer this question, you need to know, what is this book? Who wrote the book? Why did he write the book? All these kind of difficult questions. But if you just put this question at Google as it is, just try it, you get it as it is, you would immediately find this particular paragraph where a specific sentence tells you exactly what was the inspiration for this particular book. So my point that I'm trying to make is how hard machine needs to work to find the information. When we are assessing the difficulty of the questions, we're thinking about ourselves. That maybe some of you haven't even read this book, you know, how much time it will take you to discover it. But since machine operates and can very easily perform big searches, powerful word matches, this is an easy task for the machine and difficult task for a human. However, let's look at another task that any of you who speaks English should be trivially be able to solve it, which is text comprehension or machine reading. It comes by different words, but the idea is the following. You are given a paragraph and a question, and then you need to select one of plausible answers. So in this case, we have Sally liked going outside, she put on her shoes, she went outside to work. And in this case, the answer, why did Sally put on her shoes? Because she wanted to go outside. So any person with the logic would understand why did she put the shoes. For machines, actually, they're not doing very well. It's like 70s, in 70s on this task, because it requires reasoning, because the information that it needs to find to connect the dots is not readily available. And again, if we will provide machine with million stories of this sort with an answer, the pattern will be there. But if the pattern is really hard to get, because it's not available, it's not just string matching, it's still plenty hard for the machine. So this whole assessment of asking, you know, machines can do processing, you know, when we compare it with humans, they just have different capacities and capabilities, and we need always to analyze it in context. Let me give you another example that was mentioned in the slide by Dan Juravsky, relates to summarization. So here there is some story from CNN, and I will show you on the next slide a summary produced by a journalist and a summary produced by a machine. So I would give you a minute to read, and you know, if you are representative of, you know, typical students that I'm teaching at MIT, they would have no difficulty to say that the first one is written by the journalist because it's much more compact, and the second one was written in quotation by the machine. I mean, it's still, you know, it's not as fluent and compact as the human one. It's pretty reasonable summary. You can say, wow, machines are doing a great job in understanding natural language, correct, producing such a summary. But the truth is that in this case, machines were trained on a simple classification tasks. Many news agencies, in addition to the story, provide you story highlights when they extract some sentences or close paraphrases of the sentences as a highlight from the story. So you can just, using this data, identify some sentences as more important and some sentences as non-important, and you just train a binary classifier like the ones we've seen in this course, and you have, you know, you can use CNN, you can use any other classifier that you like, and then machine can generate you this kind of summaries. Again, let me show you an example of summary which machine can also produce. There is a place where we can really benefit from using NLP, and this is called Cochrane database. So Cochrane is a community of physicians and researchers who are interested to promote evidence-based medicine. So let's say if you are asking a question about some disease, you want to know, you know, all the randomized control studies. Let's say you're asking if zinc helps to control cold symptoms. So they would go by hand, find all the articles that did randomized control study, and then summarize them and say, this article found that in this condition it helps, and in this condition it doesn't help, and it's really comparative connection and evaluation. So this is extremely hard for machine to do. And we started, you can do some progress. For instance, I was personally interested in the question if coffee either, is it cancerogenous, increases your chance of getting cancer, has no correlation, or it actually decreases the chance. And you can imagine, so we build a system that can actually extract from the articles all these different sentences, and then you can either assess yourself, or maybe you can group them in some way. But you can see that this kind of really quantitative assessments where we need to analyze and see how the pieces of information are coming together, it's really hard. And I just want, so maybe some of you will work on this problem, and I just want to show you.
There are now so many studies being thrown around, they can seem to contradict one another. In just the last few months, we've seen studies about coffee that claim it may reverse the effects of liver damage, help prevent colon cancer, decrease the risk of endometrial cancer, and increase the risk of miscarriage. Coffee today is like God in the Old Testament. It will either save you or kill you, depending on how much you believe in its magic powers.
So in this particular case, actually NLP had resolved this dilemma as we're making more progress to actually take all these materials together, at least the materials together, and to show, the distribution between different opinions. But this is still very hard. So overall, if you're looking at industry, there are lots and lots of applications, for instance, for search, for information extraction, machine translation, text generation, sentiment analysis. These technologies are already working, and you may not be even aware. Like, let me just give you one example that not many people are aware of. Today, when you're writing your essays, when you're entering American colleges like GRE or SAT, all those that require the writing, you may be wondering how they are read. And in reality, they're read by machines. Every essay is read by a human and by machine, and if they disagree, then there is a more senior reader who resolves the dilemma. So this technology has been out there. We don't even know how much of NLP impacts our daily life. And, each time I open the news and I read some interesting things, like, for instance, there is a startup or a company now that produce data-driven narrative that explain, amplify, and illuminate significant events and outcomes. And they hope that with their automatically produced writing, you can actually improve human productivity. So there are lots and lots of different opportunities, and it's very fast-growing area. And you can not only kind of get job and make an impact, you can also make an important social difference here. Like, for instance, there are a lot of kind of community organization. They collect statistics from the databases. Like, this is a statistics, it's a website that collects mass shooting in the United States and puts it in the database in public eye so that people can analyze the database, identify important trends. And in this case, we actually built the system. We automated what humans were doing. And you can see that, it produces a reasonable accuracy in the extraction. So now I want to move to a next question. And if you notice in my slide before, the accuracy for some of these categories was not extremely high. And you can say, why machines are still not perfect? Why they cannot understand language perfectly? In general, I mean, they can do it for narrow applications, but not in generally. And I would like to move to this part of the lecture by giving you example of titles that come from the US newspapers. And I would let you think for a second why these titles are so funny. At these particular phrases, and everybody can find the funniest one, let's look at the Iraqi head, 6 arms. So the reason this particular one is funny, because the head, we have an anatomical meaning of the word head, and also we have a name of the head as a leader. And this particular phrase is funny because the word arms is also ambiguous, because it has biological, anatomical meaning, and arms as weapons. Another favorite is ban or nude dancing on governor's desk. So you can say that we are prohibited from dancing nude on governor's desk, or governor wants to prohibit nude dancing. And you can see that depending on the scope of the syntactic phrases, we can easily get these different meanings, but because we kind of understand contextually, and since nobody's trying to dance nude on governor's desk, we actually can get to the correct interpretation. Now, machine actually has much, much more ambiguity when it's trying to disambiguate a sentence. And this is an example that comes from my colleague from Cornell, Professor Lillian Lee, that found it from some companies that now is bankrupt, that was selling computers in 80s. And this sentence says, "At last a computer that understands you like your mother." And this is very interesting sentence because it can illustrate different type of ambiguities that we can see. Here, the first ambiguity that I want to show is syntactic ambiguity. Well, you talk a bit about syntax, about how different pieces of the sentence to fit together to create meaning. So, for instance, you may understand that it understands you, like your mother does, meaning understands you perfectly or not, but understands you like your mother. Or another less likely interpretation because of our context is it understands that you love your mother. So those are two possible interpretations, each one of them would correspond to different parsing of the original tree. Finally, we can also look at every individual word and see what are the different meaning of the words. You remember we already did it when we look at the word arms or the word head. So even if you look at the word which is relatively unambiguous to all of us, like the word mother, in a dictionary you can actually have two definitions. One is a female parent, another one a stringy, slimy substance consisting of yeast cells and whatever. So you can see, of course, that the first one is much more likely than another one, but there will be some context when the second one will be used. So this is an instance of what sense disambiguation, and whenever a computer tries to understand something, they can actually need to figure it out. Then there is an ambiguity of how the pieces, because sentences do not show up in isolation, they actually show up in a context of other sentences, and depending who are the friends surrounding them, their interpretation may change, and this is called in natural language processing discourse, how the sentences tie together. So let's see two possible different meaning. If you say, Alice says that they've built a computer that understands you like your mother, but she doesn't know any details. So in this case, she most likely refers to Alice because Alice doesn't know the details. Now, another completion could be Alice says that they've built a computer that understands you like your mother, but she doesn't understand me at all. So in this case, she refers to mother. So as you can see that in this case of co-reference, our surrounding impact can totally change the sentence interpretation. Again, computer has to do it. And also I want to point out to your attention that depending on the language that you are operating, some things would be harder and some things will be easy. For instance, there is a task that almost any natural language processing system starts with, which is called tokenization. You need to identify what are your units, what are your words. So in English, you can say, you know, if I just use spaces and punctuation, I'm golden, I'm done. However, in Semitic languages, like just Hebrew as illustrated here, you actually combine propositions and other things together. So the word in the country actually is written as a single word, and you need to continue separation. And it's true for some Asian languages. Another example would be named entity detection. When I told you, Alice, that when we go to Google, they sometimes show you on Google News the names of people in the news and say, what's the big deal? Those are the words that are capitalized in the middle of the sentence. But again, in some languages, like Semitic languages, names are not capitalized. It's just not used. So in this case, the machine would have much more ambiguity when it tries to make this type of predictions. And what I illustrated you here, just looking by few examples of ambiguities in this very simple, though weird sentence, that in order to be able to interpret language, we need to have two things. We need to have knowledge about language, correct? We need to understand what is the meaning of the words, how do they fit together, how do they create meaning, and we also need to know something about the world. And it's the interaction of the two that help us interpretation. And what's interesting, people took two different approaches to this subject. One approach is symbolic approach. People thought, okay, the reason I understand something, I can actually kind of declaratively specify what is there in my head, what are the grammar, what is the relevant knowledge of the language, and then let machine reason in this very rich world. And this approach was kind of very common in old AI before statistical methods came in. Another approach is a statistical view, that you say, the world is complex, it's impossible for me to write down all the knowledge. I'm just going to give to machine what we call here, training instances of tasks that I care about, and then machines should be able to learn to perform my task. We're not making an assessment, we're not making a claim that machine really understand the whole natural language, but we're just saying we want a particular task to do, let's say, spam prediction. We're going to give a lot of instances of material related to spam, and it will learn it. Still doesn't understand language, but that's something useful. And it's very interesting that if you look historically, and many of you are thinking, what is the connection to linguistics? So actually, the ideas of using statistical methods had roots even like in 50s, where the coders from Second World War were thinking about language as a coding system. But then comes this very famous article by Noam Chomsky, who was a professor in linguistics at MIT, who said that actually there is no way that machine can really deeply understand language. And his famous phrase that he used was colorless green ideas sleep furiously versus furiously sleep ideas green colorless. And he was saying both of the sentences would never appear in reality, but the first of the sentences is grammatical, the second one is not grammatical. So how we can actually, how machine can discriminate it if it never seen any? And we already know that in order for us to do an assessment, we don't actually have to see the whole sentence. We can build other tools that would enable us to discriminate between grammatical and ungrammatical sentences, even for utterances that we've never seen before. And in fact, you can very easily today, with today machine learning, predict what is the right one. But this was a very impactful article, and it kind of, in some way, stopped research in machine learning approaches for NLP for a few decades. And then what happened, another person who relates to MIT, who is really an amazing figure in natural language processing, Fred Jelinek, who unfortunately passed away, who actually comes from statistical background, who was a student at MIT and who took classes with Noam Chomsky in linguistics. He was an information theorist, but he really cared about language. So at any rate, he was the first person who came to IBM and built a hidden Markov model for speech processing. This was the first time it actually demonstrated the statistical system doing something very useful, and his group pioneered the statistical machine translation, which kind of moved it from the realm of trip on Mars to something that can be used today. But he took it to a very extreme, saying whenever I fire a linguist, our system performance improves. So for a while, like in, I guess in like 90s, it was, in the early 90s, it was very, very, conflicted area, but now I should say we are all in peace. Just to illustrate you how people were thinking about it in 70s and 80s, there was a system developed at MIT called Strudel, and in AI lab. And what the system was doing, it was just moving blocks. So you can say, move the red block and put the green on top. And the machine, if there is some ambiguity, will say which green, big one or small one. Very elaborate things. And the funniest part is that actually even today, the level of language understanding that it required to do it and to understand what is available, what is not available, how pieces carry it was really, really hard. It's still hard. And the way they solved it, they had like a very deep semantic model. They kind of introduce the world, introduce what happens when you move piece in certain direction. So you have the full model of the world, and then natural language is done on top of this reasoning. But the problem was that you really need to encode by hand all of those relations. There was no learning. And people were very enthusiastic about it for a while and tried for many domains, but then they realized you can do it for a small domain, but it would never scale up because you just can't code it. And I would tell you that on my personal example, that when I finished my master's thesis and I did it on summarization, it was such a different time that you didn't even have to put evaluation. You just show example of output, and this is an example of output from my first published paper, where there was no numbers. There was just an example of output. So the field really changed since then, and empirical revolution in the field actually happened in 90s. And the reason it happened was because Penn Tree Bank, which was a very important resource, was released in 93. So it was 1 million words from Wall Street Journal, which were annotated with parse tree. So this is parse tree. So the machine had a sentence and it had a corresponding parse tree. So then we can start thinking about it as a training process, and we can think about solving it using the methods that we know from NLP. Then many people started really, who were more algorithmically oriented, started actually looking at this task and come up with many parsers. And just to illustrate you the difference between kind of statistical thinking and symbolic thinking, let's look at the task of determiner placement. For myself and for many other non-native speakers, placing determiner like or there or nothing is actually a non-trivial task, especially if your native language differently use determiner system or doesn't have them all together. And this is a piece of text which is unique because we removed all the determiners from this text. And what they do at MIT in the class actually ask students to put determiners back. And even among English native speakers, sometimes there is disagreement as to where this determiner should be. And you can say, why? Say, oh, it's very easy because we can, determiner placement is determine, the type of noun, whether it is countable or not countable, whether it is unique, we just have, the sun, not many suns, or at least not the big sun. Is it a new, we just introduce something to this course, or old, what is a number? So there are some kind of very clear rules. So why is it so hard? Because there are endless amount of exceptions and clarifications. This is one that I found actually in a big grammar textbook I have in my office. The definite article is used with a newspaper title, The Times, but zero article in names of magazines and journals, Time. So you can really see how much knowledge do we need to be able to make the determination. Also, there is some difference between like rivers and oceans. If you're interested, you can check it out. Really kind of bizarre set of rules. It's very hard to imagine that somebody would really remember all these rules when they move to a new language, and it's really hard to encode this information. So now let's think about it in a way which is the way we're thinking about this problem after this class. We can say we're given many texts, we have noun phrases. We can just identify what is a noun phrase, like for instance, lazy monkeys versus the United States. We can encode the question, is it plural, is it a first appearance? We can ask many feature type of question, and there are 2 types of feature questions that are available. And then we can just run our classifier. I drew you here a linear classifier, but you can be using any classifier you like, maybe something much more powerful because you have a lot of data. And they took your data, like people stopped working on this problem research-wise, but the best numbers at the time were 86% of insertion accuracy. I'm pretty sure that if you try now to do it with neural models, you can go much higher. And I'm sure it's better than what I will do when I do free writing. So this illustrates to you how you can take a problem which is really hard to explain directly with the linguistic knowledge and with world knowledge. You can cast it as very simple machine learning problem and get yourself a solution. And in fact, the reason I think it's much better now, because there are even commercial packages which you can buy and they will edit your grammar. So you can see that through machine learning perspective, it's really an easy task. And here you can be thinking to yourself, oh, you're saying it's great. You know, linguists spend like decades and decades trying to write all these rules and generalization. You just run this classifier, you know, we took a package, it's all solved. So here we need to put a pause and start thinking why actually it is hard and why we may need more than just running like a classifier, just very simply. So this is a statistics which is very interesting. It comes from parsing. When you are looking at frequency of occurrences of args in parsing. And what it illustrates to, it illustrates to you severe issue related to sparsity problem. So here you're looking at unigrams, okay? You're just looking at a single arg, and you're asking in how many sentences, in how many training sentences it appeared. And you can see that unigrams, you know, as we increase the number of sentences, the coverage improves, is great. However, if we're looking at pairs, meaning we're looking at a bigger construct because they have more information, you can see that their frequency of occurrences is very low. And even if we increase our training size, we still cannot get good frequency counts. And even if you compare across languages, here I drew you a number of average frequency of the unique words and the accuracy of the parser. And what you can see that because some languages are more morphologically rich than other languages, okay, there will be languages like English which is not very morphologically rich, words will repeat many times. In other languages, like for instance in Russian, the words, because of the case system, get different endings. So if you say the dog, depending how the dog appears, it will have different ending. It would look like a different dog each time, and not each time, but there will be several types of dogs there. And it decreases the accuracy. And as you can see, that the languages which don't have sufficient frequency, which have a lot of sparse counts, their performance on the same amount of training data would be much lower than the languages which actually have sufficient statistics. So it again brings us to the point that, you know, first of all, the size of the data matters, but also matters how complex is the pattern in the data. And here, I want to tell you what happened and how the neural view changed this field. And I know that at this point of the class you already know a lot about neural models, but it still helps us to think how it changes the thinking in a specific field of study, which is in this case natural language processing. So for instance, when you're doing the parsing task, you can think about it as a classification. You have two words and you're trying to detect are they in dependency relation or not. And there are many things that you can look at. You can say, you know, what is a lexical item? What is the word itself, like in this case, it? What is a part of speech? What is it on, what are the words on the left, on the right? You can ask a lot of questions, both about the first word and about the second word, okay? And you can ask how far they are, what are the, you know, part of speech in the middle. There is a lot of choice. And people, before neural models came into play, were spending a lot of time designing it. What is a good pattern? What the combination I should be looking at? And that's how people were thinking. So the neural part, when it entered, it actually eliminated the need of do this kind of hand engineering and feature selection. So let's see how it comes into play. And I brought with me a very simple example. Let's say we are looking at how we can encode a document. Okay, now I'm talking about the documents. You remember we talk about bag of words representation, which just records, you know, if the word is present or absent. We can do frequency, but let's just for simplicity assume we maybe are just counting, you know, absent or present. Okay, so you can imagine that in order for me to get this kind of bag of words representation, I just represent every word as one hot vector. So the dimensionality of the vector would be the size of English vocabulary, and for each word it would have its own dedicated place, and then the bit will be on. Let's say for the word I, we will always keep the first place. It shouldn't be this way in life, but here with just following the illustration, I would be on, okay? Love, which is good, will be second, and so on. And then we got this bag of words representation. And this bag of words representation was like a walking horse, because now we can take this bag of words, run our classifier, can make a prediction. Now, why it is a problem? Let's say you have a document a classification task, and you want to predict whether the document talks about animals or not, okay? So here you have I love dogs. You train your neural net, and now you know to predict that, each time when we see the word dog, so maybe poodle or whatever, it's likely talks about animals. But what they want to give you during test is the sentence, the Samoyed is lovely. Now, Samoyed is a type of dog. For those of you who haven't seen, it's like big, white, beautiful dogs. Check them online. Now, Samoyed is definitely an animal, but the problem is that you've never seen this Samoyed in your training data, correct? And most likely what will happen, it will not treat it as an animal. So what we want to do, ideally, we want to move to this whole view of word embeddings that you already discussed with Tommy, where we take one hot representation and translate it into a vector, into dense continuous vector, okay, in such a way that now the distance between the word dogs and Samoyed will be very close to each other. Originally, if we're looking at one hot representation, the distance, if you look at cosine distance between dogs and Samoyed, will be the same as between dogs and lipstick. But here, we actually are interested in a transformation which will map them to some new space where these vectors are going to be very close to each other. And in the other parts of the course, you actually talked about how you can be constructing these word embeddings. I just want to remind you briefly that in this case, we can say we don't need in some ways annotated supervision. We can just take a large amounts of English texts, okay, and look at the language modeling task. What is language modeling task? That let's say I give you the two words, like I drink, and you need to predict what will be the following word. In other words, you need to give probability distribution over all the words of English. What is their likelihood to follow the phrase I drink? And when you are estimating these models, what you already discussed in the class, you can actually, for instance, take one of the hidden layers and represent and use it as an embedding of the word of interest. And if we can see it in the case of English, actually if you build these embeddings, and there are many tools to do it for you today, here you can see the 2D projection of these embeddings, because at the end those are vectors in some high dimensional space. You can project them in 2D and see how it looks like. And here you would see what's interesting, that all these words related to a bathroom and stuff, they are clustered together, and all the words that are talking about like tools are clustered together, and so on. But obviously it looks it looks very interesting, because we're thinking this is a machine that has no human clue of what is a battery or charger or whatever. But in a smart way, we build a model that you can utilize the co-occurrences of the words, and from there to learn how to represent them in a way that semantically similar words are actually close to each other. And this can help us to resolve the problem of Samoyeds and dogs, because instead of using one hot embedding, we can one hot representation, we can actually use embeddings. So now I solve kind of one part of the problem, which is, okay, now these embeddings would give me the word representation, correct? I have a word representation. How do I construct a representation for the sentence? And some of you may say, oh, do the same thing as you did in case of bag of words, just sum them up. And this is an option. You can just sum them up, and it will be a representation for the sentence. But we always want to have something better. And in this case, we can actually say maybe we have a smarter way to combine these individual vectors of the words into a sentence that it actually reflects its meaning. And again, you covered it in more detail, but here I want to emphasize it more in the context of natural language, the connection to recurrent neural networks. So one very common way people today use this representation. It comes from, you know, this is like a Lego piece that it's kind of a tiny neural network that takes current context, you add a new word, it does the computation and produces you new context. So in this case, you start with, let's say, your original context is null, you read the word I, you process them, and you move to a new state. And then you continue doing so until you build yourself a sentence as a vector. And you can say, okay, how exactly this piece trained? You train this whole system based on the task at hand, whichever task you want to solve, because here we will estimate all these weights based on the classification task you want to resolve. And maybe depending on different tasks, you're going to get different vectors. How is it different from just using the, you know, the summing the vectors? Because here you can actually capture the important components of the state that you need to know. For instance, if you're just summing the pieces together, there is no way your model will take proper care of negations and other things. But while we're aggregating this information in a smart way as needed for our final task. And this is done by this piece which is called encoder, which takes your English or some other language text and translates it to a vector. What is actually more interesting here, that now you have the whole meaning of a sentence as one vector. And it's so powerful that you not only can solve a classification task, you can actually stick to it something which is called decoder, which can take this vector and then roll it in a similar fashion and generate you a sentence. And in this case, if your decoder is trained on Spanish, you would be able to start with Spanish, translate it into this vector, start with English, translate it into a vector, and then decode it in Spanish or in other language. And that's exactly how this encoder-decoder architectures are used today in machine translation. The system is used sequence-to-sequence model. So I illustrated you some ideas how the neural models gives us totally new way of thinking about language, of how to represent the semantics of the language, how to do the composition of the language. And I would like to close this lecture by saying there are lots and lots of exciting things that are happening in NLP every day. And I'm sure by the time you are watching it, these numbers are going to be better. This is a very fast evolving field nowadays, and I'm really happy to be part of it.